Good morning. Right, so let's do some revision on some problems of some kind. I've been sent one question through, and I could look at those first, or I could look at perhaps I'll look a bit first at the homework that's just gone by. And so this question asks you to compute the cardinality of some sets of functions here. What's the cardinality of 1? So the set of all order isomorphisms from rationals to rationals. And then part 2 says set of all continuous functions F from R to R. Okay, so how does one go about this? Well, of course, an order isomorphism, so it has to be an order preserving map, and it has to be a bijection. So certainly any such function here is an element of Q to the Q. Right? So the set of all such functions. So this is going to be a subset of Q to the Q. So this has cardinality. Right? This is countable and this is countable here. All right, so this is the size of aleph 0, collection of functions from aleph 0 to aleph 0. And this is the same as 2 to the aleph 0. So this is an upper bound here. Right? So now you need to show that this upper bound, in fact, is correct, right? So you need to show that there are at least 2 to the aleph 0 such order isomorphisms, and then we'll get this exactly this. So we show that it's exactly 2 to the aleph 0. So I need to somehow get an injection, a one-to-one map of a set of size 2 to the aleph 0 into the collection of these order isomorphisms here. So this is one way. I mean, I'm not saying that this is so we do this by showing that 2 to the aleph 0, right? And this cardinality of the power set of omega is a lower bound here. So for each subset of omega, I'm going to find a different order isomorphism, right, here. So I say let X be a subset of omega be arbitrary, we just have to find some way of, for each x, thinking of a different order isomorphism. So this is one way to do this. So we define an order isomorphism, f, which depends on x, by, well, let's just say that on the negative half line, it's just the identity. Right? So we're only interested in the action of f on rationals in here. So we don't do anything interesting on the negative rationals. But then on the positive rationals, so I mean, somehow the idea is, so down here, it doesn't do anything interesting. Right? And what we're going to do is, if a particular number is in X, right? If K is in X, right? The function will be like y equals X. So if K is not in X, then it's going to look like y equals X. Right? On the other hand, if K is in X, right? So here it would grow as between K and K plus 1, it just grows like y equals X. If K is not in X, then we just make it do something different, right? We'll just have it grow slowly for the first half and then speed up in the second half. So to this K plus 1. And then we ask whether K plus 1 is in X. And again, so we grow it again as y equals X if K plus 1 is not in X. Then, for example, if K plus 2 is in X, we have it grow slowly and then a fast here, so that it now gets up to K plus 3. So we just have to specify this somehow. Okay, so here is one way that works. So I just specify this. If K is not in X, then f restricted to K plus 1 here on the rationals is just, again, the identity. Sorry, not the identity. Sorry, I printed something out with the right. I printed something out with the right numerology, but I now seem to have lost. Okay, here's an expanded picture. I'll just describe the picture again, and you can find the numbers. Right, so here's K and here's K. Here's K plus 1, and here's K plus 1. So if K here is in, if K is in X, we wanted to go from here to here. But let's just suppose then up to K plus a half, we'll have the slope here to be 1/2. And then from K plus a half, to k plus 1 will have the slope to be 1.5, 3/2. Here's k and k plus 1. Here's k and k plus 1. Okay, so I leave you to write down what these actual equations of these lines are. And if k is not in x, we just have it go at slope 1. So we specify then here how the function behaves between any k and k plus 1, right, on the right-hand side, on the positive side. And then on the negative side down here, it's just the identity. So it's just a 0 function. Oh no, that's not going to work, is it? Because it's supposed to be 1-to-1. Okay, so we can just let it be. Yeah, we can just let it be the identity. Sorry, I'm just drawing it wrong. So it's just like this. Right? Still like the line y equals x on the negative half line, and then it behaves according to this recipe here, depending on whether k is in or out of x. So the point of this is that for every x, we get a different function. Right? If I change x, it has to vary on, has some k is going to be in it or out of it. Then we vary this function here. Okay, so I haven't written the equations down. Okay, so the point is, right, if x is different from y, then f of x is different from f of y. But what I described there was order-preserving isomorphisms. So hence, 2 to the L of 0 is the cardinality of the subsets of omega here is less than or equal to the cardinality of the functions. Okay, so this is the actual cardinality. Hence its cardinality is exactly 2 to the L of 0. Okay, that finishes that. Now, the set of convergent functions, sorry, the set of all continuous functions. Well, prima facie, you might think, okay, it's the same as this, right? And this, which is 2 to the L of 0, right, to the power 2 to the L of 0. And let me just do the cardinal arithmetic there. By rules of exponentiation, rules of multiplication means it's the larger of the two. This is larger than this by Cantor, so I end up with this. But actually, this isn't the answer. Right? This is the cardinality of the set of all functions from R to R, but it says continuous functions. And the point is that a continuous function is actually determined by its action on the rationals here. Continuous function because for an irrational, the value of the function at the irrational is just the limit of the values of the functions to any rational sequence approaching it. I pick any tau in R, then f of tau is determined by, because it's continuous. So it's determined as the limit of f of Rn, where Rn tends to tau, each of the Rn is in Q, is any rational sequence. So it's kind of almost like a trick question, right? The continuous functions are determined by their restriction to rationals. But here then, the collection of such functions, right? But here there are 2 to the Aleph 0 maps. By the first part. Because actually in the first part, the function I drew on the graph was indeed continuous on the rationals. These fx functions here. So I deliberately drew these as rational continuous functions so I could apply them in this part. So the answer is the same as the previous part, 2 to the Aleph 0. Okay, so the set of all convergent sequences of real numbers. Well, convergent series, I suppose I should So, of course, this sum here, whether it's finite or goes off to infinity or minus infinity, is determined basically by the omega sequence A0, A1, A2, A3. Right? Clearly, this here is determined by A0, A1, A2. So there are no more such series than there are functions from omega into reals, like this here. So, and again, this has cardinality 2 to the Aleph 0 and to the power Aleph 0 here. So again, rule of exponentiation and cardinal multiplication. So again, this is an upper bound, right? And is it a lower bound? Well, I realize that what I've done in the text is I've written a slightly different answer. This should be a lower bound as well. Okay, but for every real in R, so it's just a piece of analysis, we can find a series AN whose sum is R. So, and there are 2 to the LF 0 such R's. To the LF 0 such R. So 2 to the LF 0 is in a lower bound. So the answer here is exactly 2 to the LF 0. Okay, so I just leave you to justify that for every R, I can find a power series that converges to R. Okay, so that's 443. Okay, it's another query for, okay, 5.1. Right, so sorry, I'm just trying to find it. Show that AC is equivalent to the uniformization principle. So this is the axiom of choice. Here, this is the uniformization principle. So UP here is I've got some relation R. So here's some relation R. It's contained in X cross Y. So the uniformization principle says for any situation like this, I've got a region contained in no matter what X and Y are, there's a function that uniformizes it. So the domain of F is the same as the domain of R here. So for every X for which there is something above it in this region, right, the function will pick out F of X here. It'll pick out a Y that's so that the pair X, Y here is in R. So that for all X in the domain of F, pair x, f of x here, this is in the relation. So if you like, when I look at the projection of the graph of the function onto the x-axis, I get just the same projection if I took all of the whole region down onto the x-axis. That's what I mean by saying the domains are the same. Right? So what the function does is pick out one thing on each of these vertical fibers that's in the region. So that's the key to the choice part. I just look at each of the fibers above each x, which are in the region, and the choice function from the axiom of choice will pick out an element for me, and that'll be my function. So that's the idea of the left to the right direction here. So I need a family of sets, non-empty sets. So these XUs will be here. So for a U, this will be XU. Sorry. For a U here, this will be XU. This is the set of V's such that U and V here are in R. So for a U here, these are the V's. Then G is a family of non-empty sets. By AC, there's a function f. Such that for any XU in G, f of XU is a member of XU. So what is that doing? For each U, it's picking out a V here. But then what have we got? The domain of this F is the domain of R, right? And for all U in the domain of F, F of, well, this XU here is in that F bar. I mean, strictly speaking, let's call this F0, right? Then the domain of F0 here is then define. We'll define a domain of F function, which has got the domain of R, by for all U in the domain of F, we'll have that F of U is this F0 of U. It's F0 of XU. Then for all U in the domain of this F, U FU is in the region. Sorry, this got a bit messy. Okay, the other direction. We've got to use this idea, uniformization, to find a choice function for a general non-empty family of sets. So what we'll do is try and, well, dress it up so that I can apply UP. So let G be a family of non-empty sets. And we want a choice function for it. So we want a region. So consider R, and it will be contained in G cross union, big union of G. Okay, so first element of a pair here is going to be one of our non-empty sets. And the second element is hopefully going to be something in all of these sets smushed together, the union of all of these sets together. And we're going to have XU in R. I still have to specify what R is going to be if U is in X. So you can see that what I'm doing is just something like this. Here is G, here is the union of G, here's a typical X that's in G, right here. And I just write the elements of X out here. Here's another one, X prime. And here are the elements of X prime written out like this. So this constitutes my region. And now the uniformization principle gives me a function. So of course, what the function is doing is just picking an element from each of these X's in G. And that's what we want. So I'll just say here, a function that uniformizes, okay, this R is a choice function for G. Here, as it goes across. Okay. Let me look in at 5.3. Show that the well-ordering principle is equivalent to cardinal comparison. So cardinal comparison says here, for any X and Y, either there's a one-to-one function from X into Y, or the other way around. Okay, so what can we do here? So the well-ordering principle, well, that's useful for lining up any set with an ordinal. So if I line up my sets X and Y with ordinals, I've got a hope perhaps then of finding some injective functions one way or another. So I'll take a function g that maps x 1-to-1 to the ordinal gamma, and a function f that goes from y to some ordinal delta. Here. So one of these is less than or equal to the other. Let's suppose delta is less than or equal to gamma here. So what I've got is my x, let's see, how shall I draw it? Here's x, and here's gamma. So I've got this function f, sorry, I've got this function g going this way. Here's gamma, here's delta, and here's y. And I've got this function bijecting y with delta. Okay, delta's, oh, I've drawn it here as delta's greater than or equal to gamma here. Okay, let's make gamma longer. Yeah, so x goes up here. So what we do now is just say, okay, I can map y 1-to-1 into x by mapping it 1-to-1 into delta, which after all is just a subset of gamma. And because this is g is a bijection, I can invert it. So I'll apply g to the -1 to f on y. Yeah, I do f, which is going to send y into delta, and then I do g to the -1, which is going to bring it over to x. And this is 1-to-1. And if it's the other way around, then I similarly get a function going from x 1-to-1 into y. So then we similarly get a function in the other direction. So that gives me the left to right direction. Okay. Now I've got a set that I need to well order, and I've got the cardinal comparison principle. So let X be any set. I think if you now look at corollary 427, there's an ordinal nu, so that nu is not injectable into X. But by cardinal comparison, this means that X is injectable into nu. Here. So now I can well order X. Here's X, here's nu. I have a 1-to-1 function going in this way. whose range is contained in nu. Right? But I can use the well ordering on nu to induce a well ordering on X. I'll take two things, A and B and X, and I'll put A comes R before B, if and only if, let's call this function here going here F, if and only if F of A is less than F of B. It's an order preserving map. As this is a well ordering, and this is a well ordering. So then R is a well order of X. Here. Right, it's a question. Is a function in the axiom of choice a set? Yes, we want, in the axiom of choice, we want a so-called choice function. So the function, what we've got is a bag of sets. Here are the different sets, non-empty sets here, X and Y. So AC says there's a choice function, which I take is what this question is about. So there's a function F so that it picks out one element of each of these sets. What is the difference between functions that are sets and functions that are not? Well, a function is a set or a class of ordered pairs. So a function is always a set unless it's too big to be a set. It might be a proper class. So after all, what is a function? It's a class of ordered pairs. I mean, we may have a function that goes from V to V. For example, the function X that gives a singleton X here. Right? That's defined on all sets X. So in that case, the function F is this class, for any X in V. So it's a class, proper class of ordered pairs. So in this case, the function is a class. But if it's not a proper class, then a function is always a set. So if it's not a proper class, then it's just a set of ordered pairs. So in some sense, there's no difference between a function that is a set and the one that's, defines something by transfinite recursion. By transfinite recursion, if we do this on all of odd, all of on, then we're defining some function h from On into, well, V or whatever it is. In general, this will not be a set because its domain is a proper class. But if I define a function by transfinite recursion on omega, for example, I get something that goes from like omega into V here. This is a set, right? But in both cases, they're classes of ordered pairs right here. Another question was, in AC, can the family G be a proper class rather than a set of sets? Right. Well, if you did that, you'd be asking for a stronger principle. And it can be shown that it's a strictly stronger principle. So officially speaking, AC is only about sets G here. Okay, not proper classes. This would be a stronger class choice principle. Allowing G to be a proper class of non-empty sets would require a stronger choice principle. So it's a provably stronger choice principle. Okay, and that's not on the cards for this course. We're talking just about AC where G is a set. So the answer briefly is no.